Hi, hello everyone. Thanks for your time to join this session. My name is Xiaoyang. In this session, I will talk about the multitask and multi-domain modeling in Pinterest Ads Retrieval Ranking team. This is a teamwork from many contributors in our team, including myself and Peifeng, Abe, Yang, Jay, Ashman, Pat. Okay. So firstly, let's go briefly talk about the background. I think this is a brief summary of our current ads delivery funnel. In the very beginning, we have the targeting, we have different candidate generation, we have the pacing and budgeting and deduping stage. And then on top of that, we have the retrieval ranking or lightweight ranking, where we try to select the top K number of candidates. After that, we have our full ranking stage where we run a more sophisticated model to get the predictions. And eventually, we have the auction stage where we consider different factors and eventually decide the winner of the auction. So going back to the retrieval ranking or lightweight ranking stage, in a simplified version, we are ranked by a function, what we call utility function. And this function is usually a function of the bid part and the model prediction such as CTR, click-through rate prediction, CVR, conversion rate prediction, and relevance prediction, and many other predictions. And currently, our stack, we still use the two-tower model architecture. And we used to have like around 10 production models for different services or what we call domains and different tasks. That's our kind of the status before we started this effort. And there are several problems we observe. The first problem is that we have a data fragmentation problem. For example, because we have different models for different domains and different tasks, like we only use the data from a single domain to train a model. And more concrete example include that, like for example, if we want to predict the outbound click-through rate, in the past in our retrieval ranking models, we only use the training example from the outbound click ads. So we could have like 100 more x more training data if we include all kinds of eligible ads. And similarly for video predictions, we could have like 500 more training examples in terms of the volume. And also for a single training example, because we have separate models for different tasks, we are not leveraging the information from multiple labels. So we could leverage more of label supervision signals. And also lastly, for a single user and single pin or candidate, we actually have different models. So we have different sub-segmented training data to learn some embeddings for the ID features. And the second problem is that we actually have very naive handling of domain-specific features. And there are certain domain-specific features, like there are shopping-only features, there are wheel-type-only features, there are opt-in, opt-out user-only features. And whenever we have such missing feature issue, we will treat them as missing and use some default values. So that means we could have more sophisticated way to tackle this domain adaptation problem. And the third one is that because we have like very segmented training data, we could actually once we have significantly larger training data, we could also significantly increase the model size to really leverage the larger training data. And lastly, like practically, this is a maintenance and velocity issue. Because we have to maintain so many different models, it's a burden for the maintenance. And also, whenever we have a new model architecture innovations, we sometimes need to apply the same innovation in multiple models through multiple launches, which requires some extra engine time. We could save that time to do more and new innovations. So observing all of those aforementioned problems, we want to propose some new kind of models. And in one sentence, I think our goal is to have a multitask, multi-domain modeling, where we can have a single model to predict all the tasks on all the domains. And in practice, eventually we end up having two models, one for the all of the on-site action predictions and one for all offset action predictions. But still, we significantly reduce the number of models. And here are some details of our model architecture. In the very bottom is all of our input features. They are basically it's a set of different features. And we first feed all of those features into a domain adaptation layer, which tries to get different representation for different domains. And after that, we have a separate head or separate towers for each domain, what we call domain-specific tower. And next part, I will go deeper into this domain adaptation layer. This layer, generally speaking, consists of two components. The first component is a domain-specific batch norm layer, where it is applied to all the scalar numerical features. But this batch norm is not shared across domains. And the second component is what we call a squeeze and exile night that tries to learn the weight of each individual feature and use that weight to get a kind of like a weighted sum or attention style combination of features that can be used in downstream of the model. Those two components consist the domain adaptation layer. And after that, we basically have different tower for different domains. And inside each domain-specific tower, we are basically using a multi-gate mix of expert architecture. And in the very bottom, you can see kind of 5 rectangles. And for the first one, it is a neural network that is only specific for this task A for this specific domain. And this is like what we often refer to as task A expert. And similarly, we have a task B expert. And in addition to those experts, we also have a task A across domain expert. So the weight of this sub-neural network is shared across different domains, but all used in task A. And similarly, we have a task B cross-domain expert, where the weight is shared across domain towers, but all of them are used in the task B. And finally, we have a domain expert. This is only, the weight is specific for each domain tower, not shared across domains. So after we have those kind of expert, we use a gating network to decide how to find the gate of different experts. So it's a mixture of experts. And after the gating net, we have different and separate head for each task. And finally, we have the prediction for each task. And also, we have a shallow neural network for calibration, which is omitted from this figure for simplicity. And next part is the evaluation part. So basically, once we have this new model architecture, we try to conduct the offline evaluation on all kinds of domains and all kinds of tasks. So basically, our test loss is defined as the same as training loss, but on the next training intervals data. And our current loss function is used as the distillation loss. And you can see that on every single domain and on every single task, for example, for home fit domain and for CTR task, the new model compared with the old production model, in the test loss, we were able to reduce the loss value by 20%. and also like this trend is similar across different domains and across different tasks. And the last one, we also significantly reduced the test loss on the CVR task from a separate model, the offset model. But overall, you can see that on all the combinations, we are able to reduce the test loss significantly. And we also, as mentioned, as in the problem section, we are, after we have a much larger training data, we are also specifically want to increase the model size. For the embedding part, we actually didn't do much because there were several different production models, and each production model has like varying size of the embedding tape embedding feature parameters. So kind of on average, like we increase the embedding size by 1.1x to 2.6x, depending on comparing with which baseline model, production model. But on the non-embedding side, non-embedding part, we significantly increase the size of the parameter from 6x to 90x, depending on which baseline model we were comparing against. So this part for the model size. So because of this model size increase, we also spend some time on the infra side to make sure in both training infra and serving infra, we are able to train this model. For example, on the training side, we need to invest more on the multi-GPU and training, and also other techniques to speed up the throughput of the training. And for the serving time, we also need to, we actually made several changes. Firstly, we need to make some infra changes to support this multitask model serving, because at each time there will be, the model will output more than one output. So there are some infra changes on that part, and also we are making sure we're able to serve this larger model. So finally, we conducted the online A/B test in our Helium platform. So these are some results on overall ads results. So we are able to increase the CTR by 2.4%, and we are able to increase the GCR30 by 3.0%. Here, the GCR30 is the click-through rate, where the click-through duration is larger than 30 seconds. And lastly, we have this, we increase the outbound click rate by 2.8%. And lastly, we increase the conversion rate by 3%. That's from the online results. So now I think it's the Q&A section for this part. Yeah. So first question is, does GDPR affect which feature you can include in your model? Yeah, I think that definitely has the implications. I think that's one of the reasons that eventually we don't have one model but have two models. One is for a lot of onset action predictions, and another is for a lot of offset action predictions, because there are some different privacy requirements for different task models. So by having two separate models, it allows us to kind of comply with all the requirements. Okay. Next question. Do you experience interference between tasks or domains? Yeah, I think that's a great question. So we, like in the very initial launch, I think because of the gain is large on every domain, every task, we are able to improve. But I think this is a valid question, and later in some early exploration on further improvement, we did see some signs of this kind of issue. And I think these are also not specific for Pinterest. It's a very active research area to discuss about this part. there are several papers like Pareto efficiency or some other things. And we also try to, for example, use different weight for different tasks or domains, and even for separate models. But the architecture is still multi-task, multi-domain. But because you can have separate models, you can emphasize on one of the tasks that will be used during serving time, and you just use other tasks as a auxiliary loss, or kind of one one type of regularization, and don't use them for serving, something like that. The next question is, do you have a higher inference cost? I think definitely yes, but the good thing is that right now we are still having a two-tower model architecture. So on the query side, during inference for each single request, we only do inference once. So even though the model size increased a lot, and even though the model size increased a lot, the infra cost is not increased that much. But we do have increase, but not too much. The next question is, how balanced are the data for different tasks? I have experience showing that using different sizes of data of different tasks will impact the performance of them. I think this is also a great question. Like naturally, in our case, probably also in many other cases, the data volume are different from different domains, and so we also observe that for certain domains, the improvement is larger than other domains. For example, if one of the domain has the least number of training examples, then the gain might be slightly smaller. And so we also are trying to play with different weighting algorithm or other things. For example, we can regularize on the grid. There are some papers, for example, regularize on the gradient part to make sure the gradient from each task or each domain are kind of on par, or something like that. But this is some area we are actively exploring. Yeah, thanks a lot, everyone. I think we have on time to take a break. Thanks, everyone.